The demo application used in this course is composed of two separate microservices-style component applications, the Guestbook front-end application and the Guestbook backend service. With the initial default configuration, the two components communicate through the local host network, assuming that they're both running on the same host. Both components are written in Java with Spring Boot. The initial configuration of the components does not integrate with any Google or other cloud services. The application can be run on any platform that has the appropriate Java edition and related libraries installed. The initial demo can be run on any such machine, and that includes Cloud Shell by launching the front-end application and backend service in two separate console sessions. The Guestbook application delivers basic CRUD functionality, although only the create and retrieve functions are used. The update and delete functions aren't implemented because they're not needed for the purposes of the demo. The front-end application provides a simple web form that allows a user to post a message composed of a username and a message body. When a message is submitted by the user, the front-end application sends it to the backend service. The backend service then creates a new record to store the message. The front-end also displays a list of previous messages retrieved from the backend service. The demo application follows a classic three-tier web architecture. The front-end application sends messages to the backend services to create, retrieve, update, and delete records. The single backend service in the demo sends responses back to the front-end and uses a database service for storage of the message content. The application is initially configured to use an embedded HSQL database. Persistent database storage can be implemented using MySQL or a similar database service to replace the embedded HSQL database. In the first lab, you'll use Spring Boot to configure the application to use a Cloud SQL instance for the database functions that it needs to store and retrieve structured data. Although the demo application is quite simple, it allows us to demonstrate how to implement distributed tracing using a system like Zipkin. Zipkin is able to provide detailed timing data that can be used to troubleshoot latency issues with a microservices-style application like this. By implementing a Zipkin or similar solution yourself, you can provide the tracing services required to handle both the collection and analysis of this data. In the labs, you'll use Spring Boot to configure the application to use Google's fully managed Stackdriver Trace solution. This enables you to implement tracing for your application without having to deploy and manage your own tracing services. The communication between services is a critical component of a microservices framework, and a message queuing system is critical to ensure reliable scaling. Message queuing solutions like RabbitMQ allow services to send or receive messages or requests asynchronously, instead of having to carry out resource-intensive processing at the same time. This helps to avoid component services getting stuck waiting to hand off a message. Message queuing makes it much easier to scale out component services independently because it allows you to distribute the messages to multiple targets for processing or across multiple services for load balancing. Message queuing also helps create connections between applications or services that are more independent, asynchronous, and therefore less tightly coupled. In the labs, you'll configure Cloud PubSub as a message broker for the application. The front-end UI sends messages to a message queue that the backend service is subscribed to so that it can receive and process the messages asynchronously. Runtime configuration services allow you to define a centrally managed data store containing key-value pairs that are used to provide configuration details for components within an application. These values can be dynamically updated, and in a typical scenario, a runtime configuration service would be used to contain the names, addresses, or connection details that allow components within a microservices application to identify and locate each other. This is particularly useful for microservices applications where component services may need to alter their behavior based on the status of other services. In the lab, you'll use the Cloud Runtime Configuration API to store values. These will be used to allow the front-end service to locate and connect to the back-end service when they have been deployed to App Engine and can no longer communicate directly with each other over the localhost network. These infrastructure services all require management and operational overhead in order to deliver scalable solutions. In a real-world production environment, you'd need to consider the management of each of those systems, how they would need to be protected, how they need to be configured for scalability and resilience, how to manage software updates, and so on. That may or may not be practical in any given organization, but if you want to implement a solution that includes some or all of these components, that additional cost and operational overhead must be allowed for. In contrast, adopting a cloud-native approach through the use of GCP services for these capabilities, instead of building and managing your own, provides instant access to the capability without having to deploy any additional infrastructure yourself. This also avoids the overhead and complexity of managing the lifecycle of trace, messaging queue, database, and runtime configuration service servers. GCP services provides the confidence that goes with knowing that the underlying infrastructure behind all of these services is not just fully managed, but resilient and implemented on a global scale. Ultimately, if you adopt a cloud-native approach, you can leave the management of those other GCP services up to GCP and focus on what you do best, developing the component parts of your application.